For the first few minutes of class today, we are going to finish up our discussion of electric double layer, or EDL, forces, and then we will talk about the exam. Okay, so EDL forces arise not because of the like charge of the big colloidal particles, which we would normally expect would cause an electrostatic repulsion, but rather the repulsion originates from the fact that we have this diffuse cloud of counterions, and as the particles get closer together, the diffusion of the counterions is limited just because the particles are getting closer together, and that electrostatic repulsion of the counterions causes them to associate with the sides of with the surfaces of the particles, and the compression of this diffuse double layer causes a reduction in entropy and therefore a repulsive force, so that you get back to a situation with more entropy, so more statistical microstates available. When somebody says more entropy, it just means more ways to arrange things. Now, in a suspension of nanoparticles, which is sometimes called a colloidal suspension or just a colloid, so as nanoengineers and chemical engineers, you should know the nomenclature here. A colloid is not a single particle, it's the whole flask of stuff. The colloidal suspension, you could have a colloidal particle, but the particle itself is not a colloid. Colloid is the whole thing. So in any suspension of nanoparticles, what you have is a competition between the van der Waals forces, which will dominate at very small distances, and electric double layer forces, which will produce a barrier that must be overcome, a repulsive barrier that must be overcome in order for the nanoparticles to aggregate. So if you have high van der Waals force and low electric double layer force, you have what's called an unstable colloid. It's a colloid that will eventually flocculate. That is, the particles will aggregate because the van der Waals force overcomes the electric double layer force. If the electric double layer force is high, the colloid will remain suspended. So our limiting cases, and this is called the DLVO curve, named after 4 people. What we have in the limiting cases is a pure EDL repulsion. And there are various functional forms of the EDL report, various variations of the EDL repulsion that depend on the specifics of the surface charge density and the geometry. It's way too many more details than we have time for in this class, but they all have this exponential proportionality. So the WD of the EDL, this is the energy of the EDL, is proportional to e to the minus d. D is the distance of separation. So this is the repulsive component. Do we need more lights on in here? Is this how it normally is? That looks good? Okay. Should I start over? No. Okay, so the limiting case of repulsion is the EDL follows this exponential decay. In contrast, you have the van der Waals repulsion, which emerges from the depths of hell. I'm sorry, the van der Waals attraction, if I said repulsion. This is the van der Waals attraction. And it follows some 1 over d to the n dependence, depending on the geometry. At very, very small distances, and this is WD 40, just kidding, WD total versus d. At very small d's, the van der Waals attraction always wins out. So let's draw two scenarios here. We have very small distances, we have an attraction, but then maybe the EDL force starts to win out, and then we have something maybe that looks like that. This is the primary, this is the barrier to flocculation that is produced basically by the strength of the EDL repulsion for a given scenario. And what gives you this scenario? So this is we would call this a stable colloid. Stable compared to what? Stable compared to the alternative curve that I'm going to draw in a minute. Stable colloid with say a high surface charge density. And low electrolyte concentration. And I'll tell you why this is important in a minute. By electrolyte concentration, I just mean take the salt shaker, dump salt in. In the case of low electrolyte concentration, don't dump any salt in, or don't dump very much salt in. What are the parts of this curve? The curve all the way at D approaches 0 is the primary minimum. If you go here, the colloid's dead. It flocculates, it's no longer a suspension. This here is the secondary minimum. Almost like the equilibrium position. It's kind of the D of separation where the particles sort of want to be under ideal circumstances. Okay, in contrast, what if we have a weak electric double layer force and or a strong van der Waals attraction? Then we might have something where there's hardly any barrier here. And we might call this an unstable colloid. So this would be a low surface charge density. And a high electrolyte concentration. So you could turn a stable colloid into an unstable colloid just by adding electrolyte to the suspension. In fact, this is used all the time in colloid science and even biochemistry, where you say, I'm going to salt out the protein or the nanoparticles literally by adding salt to the solution, and then stuff crashes out. Then you can centrifuge it or whatever you want to do to separate the solid material from the liquid. What I didn't draw here, and what you don't really need to worry about so much, but you should be aware of it, is that this doesn't go infinitely down, right? If you get super, super close, like where the electron clouds are actually impinging on each other, then the potential energy goes way up. So as the distance is exactly zero and the electron clouds of the colloidal particles themselves start to impinge on each other, then the Pauli exclusion principle takes over, because you can't have one particle pass through another particle. Duh. So that's like a repulsive force. But it's not usually drawn on the DLVO curve, but you should know that just because the van der Waals attraction is so strong at small d's does not mean that the universe collapses into itself, which is what this would imply. Okay, why should the salt concentration matter? The role of the electrolyte concentration. Picture two scenarios. One is, let's call it low salt, because salt is a shorter word and faster to write than electrolyte. And we have our two charged particles with our counterions. And this is a diffuse layer of counterions. When you push these guys or girls together, there's a repulsive force that depends on the change between how confined the counterions are in the apart state versus the together state. And the bigger difference there is, the greater the decrease in entropy from the apart state to the associated state, the more repulsive force there's going to be. Now, the reason these charges, these counterions, aren't closely associated with the particles is because of entropy to begin with. The reason why the layer is diffuse and why the counterions aren't just sucked to the particle electrostatically is because there's some entropic driving force toward kind of a diffuse layer where it's a little bit like those fish that suck onto the bellies of sharks. Maybe that's a horrible analogy, but it's kind of a diffuse layer of fish that suck onto the belly of sharks. Or like the gnats when you're hiking, it's a diffuse layer. Okay, so in this case, in low electrolyte concentration, there's a big entropic cost to confining the ions to the surface. And this gives you a diffuser double layer. And thus greater repulsive force one experiences when trying to push them together. Okay. How do we reduce the entropic cost of bringing the counterions close to the surface? Remember, entropy is the number of microstates available, number of configurations in space where these ions can sit.
Add more salt.
Add more salt. So if you add more salt, you have lots more of these dots. And who cares if a couple of them want to sit at the surface? Those are just, you're just adding a few, you have so many more microstates available to begin with that it's not a big deal if some of those microstates have confined ions to the surface. Yep.
What is confining the ions to the surface?
So let's say unconfined. And this is confined. Okay, so what does it look like if we add lots of electrolyte? And let me draw what actually happens in the system just as a mnemonic. Okay. This is fun. Okay. Now all of these ions that are now confined to the surface, all of these that were diffused before are now confined to the surface. But because we have so many more salt ions around, it's not that big a deal now entropically to confine some of them to the surface. Who cares? You know, who cares if they confine themselves to the surface? And now there is less of an entropic cost. Ions to surface. Let's say smaller double layer. Double layer, that's the length of the double layer is called the Debye length. Don't worry about that. Big Debye length here. Shorter Debye length here, just because it doesn't take as many ions to cancel the charge that is already on these surfaces. So you have a smaller double layer to begin with. This is the Debye, smaller Debye length. Less repulsion. And thus the van der Waals force wins. This is one of the more multi-step concepts that we're going to see in the whole course. So, questions about this? The origin of the double layer force is because you have a cloud of diffuse ions that sit near the surface. When you bring two particles together, you compress the diffuse layer of ions, and there is thus an entropic repulsion because you're confining them in the region where the particles come together, which is bad. There's therefore a repulsion. If you add salt to the system, there are many more ions around, so there's less of an entropic cost to confining the double layer to a smaller volume around the particles, and therefore there's less of an entropic difference in bringing two particles together. and therefore a weaker repulsive force and the van der Waals force can take over. Yep.
I'm saying this is an entropy force, so, but I'm just wondering, is there any physical force that can be designated as causing that, or do we just know that there is something causing it and it's related to entropy and it's just an idea, we don't have a physical force?
This is a really philosophical question. And this is actually a good time to kill the video.